In this video, I'm going to teach you how to model on Desmos projectile motion. And our goal here is we're going to build two functions on Desmos, so it's going to show you two different lines on your graph. One of the lines is going to show you your range at every moment in time based on a velocity and an angle of the projectile. And the other one is going to show you your height of your object at different moments in time for a given velocity and angle. Now we'll be able to find out what our maximum height is and our maximum range, but it'll also show us our range and our height at every moment in time. We could even see where that range and the height are the exact same value. Now remember, whenever we have a projectile, that means that gravity is going to be the only thing acting on our projectile. It's going to be launched at an angle, and because we have it launched at an angle, it's going to have a portion of its velocity that's going to be going to the right, because I can see that black arrow is up and to the right, and there's going to be a portion of this velocity that's acting upwards. Now, the portion that's moving left and right, there's no acceleration on that. What defines a projectile is that gravity is the only force acting on it, meaning we're only going to have acceleration in that vertical direction. Now, as it moves left and right, it's going to move at a constant velocity, and as it moves up and down, it's going to have acceleration from gravity. Now, what we want to do is we're going to come up with a way to describe how long our object is in motion. Now, if I launch this ball at an angle, I know part of it is moving left and right, so I have a horizontal component in my velocity, which is given by the cosine of the angle, and I'm also going to have a vertical component, which is given by the sine of the angle. If we're looking at our motion, I know that it's going to follow a parabolic path, and that if we're looking at just our vertical motion, so just the sine of the angle of that initial velocity, it's going to be moving upwards. And to keep things simple, we're going to say that our acceleration in this case is -10, and we're going to say that we're starting at 40 meters per second. And this is just the upward component. So remember, throughout this entire motion, it's still moving to the right, but we're only writing down here how fast it's moving in the upward and downward direction. So 1 second later, now we'd be moving at 30 meters per second. A second later, we'd be moving at 20 meters per second. Remember, we're still talking about the upward motion. A second later, we'd be moving at 10 meters per second. And at its highest point, we'd be moving at 0 meters per second before it turns around. So right here, what's happening is our object is no longer moving up or down. It has a moment where it's stopped, and then it's going to change directions and speed up. Now remember, when our velocity matches the sign of our acceleration, we have something that's speeding up. And if our velocity is opposite signs with our acceleration, it's slowing down. So throughout this whole upward path, we have positive velocity, negative acceleration. That means our object is slowing down every second. Now, as we start moving downwards, we have -10 meters per second. Now our acceleration and our velocity are matching signs. So we're going to see speeding up here. A second later, we're going to be at -20 meters per second. It's moving faster and faster in the downward direction. Next second, we're going to have -30 meters per second in the downward direction. It's moving faster and faster. Right before it hits the ground, it's going to be moving at the same speed that it started at, but in the opposite direction. So now we have -40 meters per second, and right here, it's going to smash into the ground, and the motion's going to stop. Now, the key point right here is that at our highest point, our velocity, so at our highest point, our final velocity is going to be equal to 0. And this is going to be half of our total time. So this is going to be 1/2 of the total time of our flight. What we see right here at this point right here, that's half of our total time. Our velocity is going to be 0. Our starting velocity is going to be whatever our initial vertical velocity was. Our final velocity is going to be 0 meters per second. And we're going to use this idea to come up with restrictions for the amount of time that our model could show for our projectile. Okay, so we use 10 meters per second in the negative direction for our acceleration. The real acceleration due to gravity is -9.8 meters per second squared. Now that's the actual acceleration from gravity. And what we can do is we can set up an equation that shows us what our time is based on our initial velocity, our angle, and this acceleration right here. So I'm going to use my acceleration equation. It's equal to v final minus v initial divided by time. And I'm going to plug in the values that I know. So I know that if I'm looking at just my vertical component of my velocity, my acceleration is going to be negative 9.8. My final velocity at the highest point is going to be 0. And my velocity that I'm concerned with is my vertical velocity. This is going to be v sine theta. So the velocity multiplied with the sine of that angle. And what I want to do is I want to isolate time, and this will give me an equation that shows me how the time to the highest point changes based on the velocity and the angle. So I'm going to multiply both sides by time. I'm going to divide both sides by negative 9.8. And I could see that the times are going to cancel out. My negative 9.8s are going to cancel out. I could ignore the 0. I have negative v sine theta divided by negative 9.8. I could cancel out those negatives. And what this gives me is that my time is going to be v sine theta divided by 9.8. And for my total time, I need twice this value. So the maximum time, the time that I'm in motion, is going to be 2 times my velocity multiplied with the sine of the angle divided by 9.8. That's the total time of my flight. And now in our model, what we want to do is we want to come up with a function that describes how my position is going to change in my horizontal direction and in my vertical direction based on the amount of time that my object has been in motion. So we're going to be using our kinematic equation. So think back to where we were doing those equations of motion. We have delta x, so that's my displacement. How far am I from my starting point? Is going to be based on my velocity multiplied with time. So my starting velocity multiplied by how long I'm moving, that's going to give me one portion of my displacement. But then if my object's accelerating, then I need the second term right here. So plus 1/2 my acceleration times time squared. Now the first part gives me my displacement based on constant velocity. My second portion gives me my displacement based on my acceleration. Okay, some key things to note. There's no acceleration. So I have no acceleration in my x direction. So in that horizontal direction, my range has no acceleration on it. So no acceleration horizontally, but I do have acceleration in my vertical component. So we're going to put acceleration. Okay, so in a moment, I'm going to go to Desmos. And what we're going to do is we're going to set up two equations. Both of them are just going to be this equation right here. I'm going to use that equation twice. I'm going to make one specifically for my vertical component and another one specifically for the horizontal component. And what's going to be the big difference in these two is my horizontal will have no acceleration and my vertical will have an acceleration of 9.8. Now I have to restrict the time that I can use for my models. So I know that my time has to be greater than or equal to 0 seconds. And it has to be less than or equal to my total time. So it's going to be less than or equal to 2v sine. So that'll be the restriction that I put on my time. So for both of these equations, so for that delta x multiplied with vt 1/2 at squared, I have to restrict it to being in between my time values of 0 and that maximum time. If I don't put that restriction, it's going to give me a bunch of data points that don't correspond with any actual values. Now what we're going to do is we're going to go to Desmos. And in Desmos, I'm going to just type out that equation. And remember, instead of putting delta x, we have to put a specific value that's going to be x1. is equal to v times t, so my velocity times time, plus 1/2 my acceleration times time squared. Now this is just that same equation. If I look back, I have delta x vt 1/2 at squared. I have vt plus 1/2 at squared. Now what I want to do is I want to restrict the time values that I could use. So my time has to be greater than or equal to 0. So my time has to be greater than or equal to 0, but it also has to be less than or equal to my equation. So I had 2v sine of my angle divided by 9.8. Okay, so I'm going to copy this and I'm going to put it into the next line. Okay, right now looking at it, it tells me that my dependent variable represented by this x1 is going to be equal to my velocity times time plus 1/2 at squared, so 1/2 of my acceleration times time squared, and it's limited to these t values right here. So what I want to do is I want to say that this one is going to be my range, and I want it to be dependent on my time. So this is saying that I want my y value, which is going to give me my range. So my y coordinate at every point is giving me my range. At different x coordinates, my x coordinates are going to be these times. So if you look, it has now taken time off of this bottom row. I still have it on this one because I don't have an equation that's dependent on time. Once I change this around, it'll get rid of this time. Okay, I also know that for my range, one of the caveats we had was with my range, there is no acceleration horizontally. So I come back here and my acceleration, I want to change this to 0. And now I could see that this equation right here is only dependent on my velocity and the angle. So I have my time, which is going to be represented on the x-axis. My equation just needs me to throw in a velocity and an angle, and it'll spit out a bunch of different values. It'll show me my range at different times. Now for my second equation, I want this one to show me my height. And again, I'm going to have it showing me based on my x-axis of time. Okay, a couple things that I need to change here is my acceleration. For my vertical direction, I'm going to have a vertical acceleration of negative 9.8. So I'm going to get rid of A, and I'm going to put negative 9.8. And one more thing that I need to do is I need to come up here, and my velocity is going to be just my horizontal velocity, so cosine of my angle. And right here, I'm going to put that this one is the sine of my angle. Make sure you put it in lowercase. And now we want to add in our sliders. I'll put parentheses around these angles so it doesn't take it as a product of A and T. Okay, now we're going to check out our graphs. I can see if I expand this, my red line is showing me my range. I can see my range at every moment in time. Make this even bigger. Okay, so my red line is showing me my range at every moment in time. Remember, my range is only moving in one direction and there's no acceleration. So I could see that I'm heading in the rightward direction, noted right here, and that my time is located in my x-axis. What I want to do is I'm going to give some limits to my velocity. So for my slider, I want it to go from 0 meters per second all the way to 1,000 meters per second. And for my angle, I want it to go from an angle of 0 degrees above the horizontal, essentially I'm rolling it across the ground, to 180 degrees, which means I'm rolling it to the left. So an angle of 0 is saying that I'm rolling it to the right. An angle of 180 says I'm rolling it to the left. Everything in between is giving me a horizontal launch. Or if I have an angle of 90 degrees, it should be going straight upwards, and my velocity should go, or my range should go to 0. Let's check this. So if I have, let's make it so we can see everything. Okay, so if I have a velocity of 60, I launch it at an angle of 1 degree. If I go all the way up to 90, we need to come up over here to our graph settings. make sure that it's in degrees. If we have it in radians, you'll see, like we just did, my angle as I change it, it kind of just jumps all over the place. So what I want to do is I'm going to come up to this wrench, change it to degrees. And now we can see it move smoothly. Okay, so at an angle of 90 degrees, what is my range? And I could see that at 90 degrees, I get a range of 0. So my y value, my y coordinate giving me my range is 0 at every second if I have a 90-degree angle, meaning that there's no horizontal motion. Okay, a couple things that I could do is I could also check if I go above 90 degrees, my range should start moving in this leftward direction, indicated by a negative range. And that's exactly what we see, so I could tell that my model is pretty accurate. Another thing that I want to do is, if I'm looking at my range, if I click it and I want to find out what my max range is, as I slide up, it'll stop here, but I could actually make it so it always shows me what this is. And the way that I add a point to my graph is I add parentheses, and I'm going to put my x coordinate and my y coordinate that I want it to just dot on here. It doesn't have to be on one of my functions, but I specifically want to know what my last point is on this r function right here. And the way I could do that is I know that my last point is going to be located at an x value of this, because this is the greatest time that I can have. So I'm going to highlight this, I'm going to copy it, and the greatest x coordinate I could have should be this value right here. And then I want my y coordinate. Remember, my y is when my r function is at a t value of this. So my t value should be that 2v sine theta divided by 9.8, and it should give me the function for my r. So I'm going to say my r function at that value. And now it'll give me that value all the time. If I click label, no matter what point I choose or what velocity I choose, it will give me that range. And for my height, it's a little bit easier. I could click onto my height and it will give me that point located as my maximum for this function right here. So what this tells me is that if I were to launch a projectile at a velocity of 125 at an angle of 23 degrees above the horizontal, I will get a maximum range of 1146.9, and I'll get a maximum height of 121.7. And my total time will be about 10 seconds, and my time for half of my path will be about 5 seconds. Okay, so if I wanted to find at any moment, I could see that at 1.9 seconds, I have a range of 218.6 meters. I could do that with my height. It'll tell me my height at any point. And if I increase my angle, I could actually see when these two things have the same exact value. So for this one right here, at 15.8 seconds, I could see that my range and my height are exactly the same value. I will have 643.6 meters. That means it has traveled from my reference point in the vertical direction, a total of 643 meters, and it is to the right 643 meters. Now, this model will work with any angle that we have at any velocity you can think of. You could use this to solve for any projectile question. Just remember that if I have, let's say, a velocity of 74 at an angle of 40, I could find my position horizontally and vertically at any moment. All I have to do is I click onto those graphs and I can drag, and it'll show me at any minute. Another thing I could do is I can make tables for both of these. If I want to get very specific, if I want to know when my time is, let's say, 2.87 seconds, it'll tell me exactly where my object is relative to my starting point horizontally. So I could see at 2.87 seconds, if I had an object launched at 74 meters per second at an angle of 41 degrees, in 2.87 seconds, I'll be located 160 meters to the right of where I started.